guys, welcome to day 22 of 100 days of code. Today we're going to be building the famous Pong game, and you're going to be doing this by using all of the skills that you've learned up till now. Pong is a classic arcade game, probably one of the first arcade games there ever was, and it has a really simple premise. It's basically just a ball that's going across a table, and two players each control a paddle, bouncing the ball back and forth. If you miss the ball, then the other player scores a point. Now, the history of Pong is itself kind of fascinating. It was created and written by this guy, Alan Alcorn, and he was a fresh recruit to the Atari company. And in order to test his skills, they decided to get him to create a game from scratch. And this game happened to be Pong, which became a huge success, selling loads and loads of machines across bars and pubs in the world. It eventually became so successful that a lot of these bar owners were calling up Atari saying, "Hey, your machines are breaking after only a few days." And the reason when they investigated was because the machines were chock-a-block full of money. People were putting their quarters in to play Pong, and the machine was getting full too quickly. So this is the legendary game that we're going to be building today. As always, the first step is to break down the problem. And I want you to have a go at this. Think about how you would take this Pong game that you've seen here, and which components would we need to write code for? Which components might fit well in its own separate class? And how might we break down the logic of this game so that we can solve it piece by piece? Now, I want you to take a piece of paper, take a look at the game screen right here, and make a note of which components you think could be separated into their own classes. Briefly pause the video and jot down some notes on how you might structure the code for this game. Now, I've broken this tutorial down into 8 pieces. Keep your piece of paper to hand throughout today so that you can compare your structure to the sample solution. Pong is a much more complex game than Snake, so pausing to think about the structure of the code now will help you a lot more in the upcoming lessons, and it'll make it easier for you to see how everything fits together. First, we're going to figure out how to create the screen, how to create and move a paddle, and then create another paddle so we can have a 2-player game, and then create the ball and make it move constantly across the screen, and figure out when it collides with a wall and make it bounce back, and then detect when there's a collision with the paddle to know when to bounce it back. Finally, we'll figure out when a user scores when the paddle misses the ball, and we'll keep the score using a scoreboard like before. Now, if you're feeling really confident, you can, in fact, just create a blank project, go through each steps one by one, and see if you can code up this game by yourself. But what I recommend, though, is to go along with the videos, and I'm going to explain each of the problems one by one, and you can have a go at building it alongside with me. So if you decide to follow along with me, head over to the next lesson and we'll get started. If you decide to create everything from scratch, then pause the video and start creating the game now. So to start off, go ahead and create a new project called Snake Game in PyCharm. And then inside this project, we're going to create a new main.py file. And inside our file, we're going to need our normal imports. So I'm going to say from turtle, import the screen class and also the turtle class. Now, the first thing we're going to do is we're going to create a new screen, which is basically going to be the window that shows up. And then we're going to set up our screen is 600 by 600. So the width is going to be 600 pixels and the height is also going to be 600 pixels. And notice how I'm using these keyword arguments so that it's a little bit clearer to the next person looking at this code what's actually happening here. Now, the other thing I want to change is the screen's background color. So there's a method called bgcolor, and inside here we're going to write the text black so that we end up with a black screen. Now, another thing that you might not have seen before is how to set the title of the window that shows up. And we do that through a method called title, and you can name your program here. So I'm going to call it my snake game, but you can of course call it whatever it is you want. Now, finally, at the very bottom of the file, I'm going to say screen.exit on click. So this way, when I actually run it, it doesn't just disappear straight away. And it waits for me and I can look at what's actually happened so far. So I'm going to click run and then select my main file. And once it pops up, this is what you should see, a 600 by 600 square window. And then at the top of the window, you'll see the name of your program, which is my snake game. And the background is now black. Now that we've set up our screen, we're ready to tackle the first of our 7 steps, which is to create a snake body. And we're going to create 3 squares, which are each going to be turtles. And they're going to be lined up next to each other along the horizontal axis. So let's think about this. When we create a new turtle, it has a dimension of 20 pixels wide by 20 pixels tall. And if we want 3 of them lined up next to each other, then we have to think about how we create their coordinates. As a challenge, I want you to think about how we can create this. Here we have 3 separate squares, which are each a turtle object, and they're shaped like a square, and they have a white color. Now, they're positioned so that the first one is at 0, 0, the next one is 20 pixels to the left, and the next one is again 20 pixels to the left, so that none of the squares overlap with each other, but there's also no gaps, so it looks like a whole snake. This is your challenge, and you might have to think about a few of the things that we've done before in order to achieve this. So browse the documentation, look back to the previous code that you've written, and see if you can solve this challenge. Pause the video now. All right, so the first thing we're going to need to do is to create some sort of turtle, right? So let's call this segment 1. And this is going to be a new turtle. And remember that when we initialize the turtle, we can already specify the shape. So we can either say shape equals square or simply just leave it as square. So now at this point, we should end up with a square turtle, but because it's black, when we run the code, we won't actually see it on screen. So let's change this segment's color to white. And all we have to do is write the word for the color. And now when we rerun our code, you can see a white square at the center, which is at position 0, 0. Now, the next step is to create our other 2 white squares. So let's go ahead and copy these bits of code, and I'm going to create 3 of them in total. So segment 2 and segment 3. Now here we're going to create the same thing, but we obviously have to change the positioning because otherwise we end up with 3 squares all on top of each other and we can only see 1 square because this is a 2D image. So let's go ahead and make segment 2 go to a different position. So the first thing we have to specify is the X, which you remember is the horizontal axis here. And if we want another square to the left of it, then we're going to have to go to minus 20 from 0. That way it'll be shifted to the left by 20 pixels. Let's say go to minus 20 and then the y-axis is going to be 0 because it's not going to move up or down. Now let's take a look at the result of this, and you can see we've now got 2 squares lining side by side, but the third square is still at the center. So the third segment is going to be shifted a further 20 pixels. This is centered on 0, 0, this is at minus 20, 0, then this has to be at minus 40, 0. So let's tell our segment 3 to go to minus 40, 0. And this is what we see. Did you manage to achieve this, or did you do it in a different way? Now, a much easier way of creating this would have been to use a for loop. For example, we could have created a list of starting positions, and this could contain some tuples. So we know that in order to specify where this segment should go to, we have to provide a tuple, which is a x and a y value. And we know that we can create a tuple just by using a set of parentheses and then adding values in there separated by commas. So if the first segment has to be at the center, then that's going to be 0, 0. And then the second piece is going to be at minus 20, 0. And the third piece is going to be at minus 40, 0. Now we can create a for loop. So for position in starting positions, let's loop through this list and create a new segment for each of those positions. So now we're going to create a new segment that's a square turtle that's going to be white, and we're going to get the segment to go to the position that we're currently looping on. Now we can delete all of that code, and when we run our code again, you can see we have the same effect. We have our 3 pieces. So if you can't remember how tuples work, be sure to go back to the lessons on tuples in day 18, where we talked about how to write them and how they work. But that completes our first step. We've managed to create 3 segments that will comprise our snake, and in the next lesson we're going to figure out how to get our snake to start moving by itself on the screen. So for all of that and more, I'll see you on the next lesson. In the last lesson, we managed to create our snake's body by creating 3 squares that were each turtle objects. Now in this lesson, we're going to move on to the next step, where we actually move our snake automatically across the screen without having to do anything. So this way, the snake is continuously moving forwards, and all we have to do as the user is just to change its direction. Now, how would we go about moving the snake? Well, we've already got these different segments that are created, but at the moment there's no way of organizing all the segments. They're kind of just created and placed on screen. So let's put them into a list called segments, and let's start out that list as an empty list, and then later on, once we've created each new segment, we go ahead and append it to this list. If we want something to continuously happen in our program, the way that we've usually done that is through a while loop. So let's create a new variable called GameIsOn, and let's set it to true. And while game is on, then we're going to move each of the segments. The simplest way that I could think of to move the segment is to loop through each of the segments in our list of segments, and then to get each of these to go ahead and move forwards. So let's say we move forwards by 20 pixels. Let's go ahead and run this program and see what we get. The first thing we notice is that the behavior is very weird. We've got a line that's being drawn, and that comes from each of the segments, which are individual turtles, and they're all drawing this line as they're moving. The first thing we want to fix is that line. So when we create each new segment, before we tell it to go to its position, let's go ahead and tell it to pull the pen up. This way it won't actually draw, and all that we'll see is the actual turtle pieces. So now we see our 3 turtle pieces scurrying along like some sort of weird caterpillar, but definitely not in a snake-like way. How can we fix this? One of the things that you notice about Turtle is it will first create the turtle. When it runs this line, the turtle will get created at the center position, so coordinate 0, 0. And then it will be moved to whatever position we tell it to go to. For example, for the third segment, it starts out life at 0, 0, and then as soon as it gets told to go to this position, it goes to minus 40, 0. Now we can see that happening on screen. When we created our snake body, you could see each individual piece being created and then moved to their location. Now, if we wanted to turn off that animation, then we would have to use one of the screen classes methods called tracer. And tracer takes a number as a input, and it turns the animation on or off. And when the tracer is turned off, then we can use the update method to tell our program when to refresh and redraw the screen. When we think back to the old TV monitors, the cathode ray tube monitors or CRT monitors, the way that they worked is by painting on a strip of color line by line by line, slowly covering the entire screen. And then once it's done one screen, it's going to go back to the top and then it's going to paint the pixels for the next scene. And effectively, it's kind of like how a GIF animation works. A GIF animation is composed of many images. So for example, if we wanted to animate, we would increase this line and then we would start drawing out a leaf until eventually we end up with an animation like this. Now, when that's all combined and played back very quickly, then this is the animation you see. In our game, what we could do is we could describe each of these scenes and tell our program when it should redraw each picture. So that way we could start out with one picture and then hit update and then do something else on screen, maybe move each of our segments and then tell the screen to update again to show the user the new result. And then each time we make the changes we want to happen and then call that update method to tell the screen to show a new image each time. Let's first turn off the tracer. So the tracer is a method in the screen class, and in order to turn it off, we're going to set it to 0. So now, once the tracer is off, if we actually try to run our program, you can see it's just a black screen and nothing will happen. Even though we've got our while loop and we've got our for loop and lots of things are meant to be happening, but until we call update, the screen is not going to refresh and it's not going to show us what's been happening in our code. So let's say that we decide to call update after all of the segments have been created. So right about here, let's call screen.update. And now if I hit run, you'll notice that pretty much immediately, as soon as you run the program, our snake body will show up, not piece by piece, but in its entirety. Now, if on the other hand, I move our screen.update line of code into the while loop so that once each segment moves, I get the screen to update, then this is what you're going to see. You see each of the pieces moving along one by one. Now, it's not really clear what's happening, so I'm going to slow it down a little bit. And I'm going to do this by importing the time module. Now, I'm going to add the time.sleep, and I'm going to get it to sleep by 1 second. So this basically just adds a 1 second delay after each segment moves. So each segment moves, the screen updates, and then we sleep for a second before the next time this happens. Notice how, in this case, our snake is moving piece by piece. So first this first piece, and then the second piece, the third piece, with a 1 second delay between each movement. Now, what happens if we move this screen.update to outside this for loop? So basically, we only update the screen once all the segments have moved forwards. Now, notice how our snake is moving forwards as an entire piece. It's going to move all 3 segments forwards before the update gets triggered and we refresh the graphics. So it looks like as if the whole snake is moving as one piece. Now, instead of getting it to delay by 1 second after each segment has moved, if I move this up here, then it's only going to be delayed by 1 second after all 3 segments have moved. This way, our snake is moving a little bit faster. And we can make it move faster still if we cut the amount of time that we're sleeping. So let's change it to 0.1 second sleep. And you can see our snake is now moving at a reasonable speed. Now, you might think that we've solved the challenge and we've now got our snake to move automatically forwards. But there's a problem. How do we turn our snake? Let's see what would happen if we control the snake head and change direction. Let's say that at some point we want to turn the snake so that it turns left. Well, what happens then? So this first piece is now facing up. The second piece is going to continue moving forwards, as does the third piece. Now, on the next iteration of that for loop, that first piece is going to keep moving towards north, while the second and third pieces are going to keep moving forwards because they're not going to change their own heading. We'll get this strange behavior because our snake segments are not linked. To illustrate this, let me go ahead and change the first segment, so the segment at index 0, and get it to turn left by 90 degrees. And notice when I run the code, you see how that head is moving in a circle all by itself, and the body has completely left the head and has continued to go forwards. So how can we solve this? Well, we have to rethink the way that we move our segments. Again, we have our 3 segments, but if instead of moving everything forwards, what if we get our last segment, so segment 3 in this case, to move to the position of the second to last segment, and then the second segment to move to the position of the first segment, and then the first segment itself to go forwards by 20 paces. And if we go back to that situation where we're trying to turn our snake, then in this method, it will still continue to work. So we've got our 3 segments, 1, 2, and 3. Our third segment goes to where the second segment used to be, second goes to where the 1 used to be, and then the 1 is going to turn and then move to the left. Now, the next turn is the interesting part, because at this point we saw how if these 2 pieces just continue moving forwards, they're going to move away from the head of the snake and it's going to move in opposite directions. But using this method, our third segment is going to move to where the second segment used to be, the second goes to where the first used to be, and the first continues moving forwards. This way, our snake has pretty much straightened out, as you would expect this snake to behave. Now it's just the matter of actually implementing this, which is the hard part. So I'm going to go ahead and delete the part where I told the snake to turn left. And I'm going to delete this for loop, which just moved each of the segments in our list of segments forward by 20 paces. Now, instead, what I'm going to do is I'm going to create a for loop, but this time I'm going to loop through each of the segments going from the last segment to the first segment. So basically in reverse order. Now, to do this, I'm going to use the range type of for loop. So I'm going to say for segment number or segnum in the range, and this range is going to have a start, a stop, and also a step. So the start is the number that we're going to start the range from. The stop is where the range is going to end, and the step is how we're going to get from the start to the stop. For example, if we wanted a range of 1, 2, 3, then of course start is going to be 1, stop is going to be 3, and step is going to be +1. Now, if we wanted a range of 3, 2, 1, however, then the start is going to be 3, the stop is going to be 1, and the step is going to be -1. In our case, what we actually want is actually to go from 2, 1, 0. So the start will be 2, the stop will be 0, and the step will be -1. Now, unfortunately, even though we have these named parameters, because the range function in Python is actually something that's not quite pure Python, it's something that comes from the C language, it doesn't actually let us use these names. I'll show you when we run our code, this is actually going to give us an error. But for the time being, it's actually much easier to visualize this as we write the code inside this for loop. So in this case, the segment number is going to be equal to 2 and then 1 and then finally 0. Now we're going to use that to get hold of the last segment from our list of segments. So we can tap into that list and then get hold of the last one using that seg num. And then we're going to set it to go to a particular X and Y position. Now the X and Y position that we want it to go to is going to be the second to last segment's position. So how can we get hold of the second to last segment? Well, we're going to get hold of the segments and then pass in seg num, but then -1. So when we first start out, we start out with 2. So the segment at position 2 is going to be the last segment, and then the segment at 2 - 1 is going to be the second to last segment. Now this one, we're going to get hold of its X coordinate, and we're going to set this to a variable called new X, and then we're going to do the same and get hold of the new Y. So we're going to get hold of the second to last segment's Y coordinate, and then we're going to use these coordinates, new X and new Y, to tell this last segment to go to the position of the second to last segment. Now, as I mentioned before, this range function comes from the C language. So if we run it with these keyword arguments, it's actually going to give us an error, and it tells us that this range function takes no keyword arguments. So while it's really nice to use it to visualize it, if we actually want it to work, we have to delete these. But just before I delete it, I want to change this so that we're no longer using these hard-coded numbers. So instead of going from 2 to 0, we want to go to the length of these segments. So in the future, if we had 10 segments or 20 segments, that our code would still work. Now the length of the segment is actually 3 to begin with, and we know that lists start counting from 0, so 0, 1, 2. The last position is going to be the length -1. And then we're going to stop at the 0th segment. So now we can go ahead and delete these named arguments. And we end up with this. And now we can run our code and we won't get any errors. Notice how all 3 of the segments went to the same position, the position of the first segment. So in addition to moving these segments, remember that we also have to move the very first segment actually forwards by, say, 20 paces. So at the very end of all of this code, outside of the for loop, we're going to get hold of the first segment, so segment at position 0, and then we're going to get it to move forwards by 20 paces. So now when I run this again, you can see our snake is now moving freely forwards. And even if at some point the snake needed to turn, let's say it turned left by 90 degrees, then our code is still going to work. Notice how our snake is now turning in a circle, and all of the subsequent pieces are following the head along its path. That's it. This is the code that will get our snake to automatically move forwards. Now, there was quite a few concepts mentioned in here, and you have to think about the segments in terms of how they move in the graph, and also this idea of getting hold of the last segment and then telling it to go to the position of the second to last segment, and then doing this for all of the segments. So it's a little bit mind-bending, and it might be worth just taking a second look at this code and going back in the video where I explained how this worked in the slides, just so that you're really clear with how this works. Once you are, then you can move forwards and head over to the next lesson. In the last lesson, we created and managed to move a paddle up and down. Now in this lesson, we're going to figure out how we can create another paddle, but we don't want to repeat all the code that we've written so far, so we're probably going to need the help of a separate paddle class. So if you haven't already created your paddle inside a separate file and a separate class, then this is the time to refactor your code so that you can create another paddle object from the paddle class easily and effortlessly. Here's what we're aiming for. We're aiming to get rid of all of this paddle related code and move it into a separate paddle class. And then subsequently, we want to be able to create a right paddle simply by creating it from the paddle class. And then we can create a left paddle from the paddle class. Now, because the right paddle has a different coordinate from the left paddle, we'll need to pass in the position of the right and left paddle as a tuple. So we might say something like the x will be 350 and the y will be 0. And on the left paddle, the x will be minus 350 and the y will be 0. So have a think about how you can make this code work and refactor this code into a separate paddle class. And this paddle class should inherit from the turtle class. Overall, our program should work pretty much the same as before, the only difference being that we now have a left paddle which can move up and down with the W and S keys on the keyboard. Pause the video and try to complete this challenge. Alright, so the first thing we're going to need is a new file, which is going to be called paddle.py. And paddle.py is going to need the turtle class from the turtle module. So let's go ahead and import it. And then I'm going to create this paddle class. And of course, all classes start off with a capital letter. Now, this class is going to take all of this paddle creation code, and it's going to carry it out when we initialize a new paddle object. This paddle object, in order for it to be a turtle object, we're going to get it to inherit from the turtle class like this. And in order to get all of the abilities, the methods, and the attributes of the turtle class, we need to get the superclass to initialize itself. The next thing we're going to do is figure out how we can get our paddle to change its shape, change its color, and all of these other things. So we can get rid of this line entirely because our paddle class is now the same as a turtle class. And then for the rest of these, instead of writing paddle.shape or paddle.color, we're going to hit Command R or simply go to Edit, Find, and then Replace, and you can take a look at the shortcut on your computer of how to get hold of this replace screen. So what I want to replace is everything that is paddle dot here in my code, and I'm going to replace it with self dot, because now we're inside the paddle class, which is effectively the same as a turtle class with some added extras. We can tap into our methods and our attributes by simply using the self keyword. Now, the very last thing we need to do in order to make this work is to go ahead and import our paddle from the paddle.py. And once we've imported it, we need to address this warning. Notice how it's highlighting this area and it's telling us that this is an unexpected argument because the paddle class doesn't actually take any inputs when it's initialized. It's just got the self here. But in fact, we do need a position being passed over. So this position is going to determine where the paddle is going to go to. Because remember, the left paddle is going to have a different coordinate from the right paddle. So now that we've fixed that, this is now completely valid code. And if we run our code as it is, you'll see our paddles being created and looking exactly the same way as before, but now we've got one extra paddle. Going down here with our go up and go down methods, ideally we would want them to live within our paddle class. So we want them to be methods inside this class. And remember that methods always have a first attribute as the self. Now, in addition, we have to again replace this paddle dot with self dot so that it's actually referring to the object that's created from this class to get its y coordinate or get its x coordinate. Now, coming back to our main.py, we'll have to modify this code a little bit because this go up and go down function is now gone, and instead we now have the right paddle dot go up and right paddle dot go down. So the right paddle is going to be controlled by the up and down keys, but the left paddle we can get it to be controlled by some other keys. Now, in our case, I'm going to choose the W key to go up and the S key to go down. So we're going to need another set of these screen.onKey method calls. But in this case, this is going to get the left paddle to go up and the left paddle to go down. And the go up is controlled by the W key and the go down is controlled by the S key. So now if we run our code, you can see that when I move W, it goes up. When I move S, it goes down, and up and down moves the right-sided paddle. So notice how now that we've refactored our paddle related code into a completely separate class, firstly, our main.py is now a lot simpler. It's clear of all of this paddle related code. And on top of that, if I wanted to create a third paddle, let's say I wanted to create a top paddle for some reason, then all I have to do is just call the paddle class and then pass in a tuple for the location of this paddle. So let's put it at, I don't know, 100 by 100. If I hit run, you can see there's a third random paddle, and I didn't have to write any of this extra code or any of the related methods. We can create as many of these paddles as we want because we've now got this paddle class. So with these examples, I hope you're getting the sense of how important classes are and just how important they are when it comes to the development of a more complex project like this Pong game. Now in the next lesson, we're going to continue building out our program and we're going to create our ball class and get the ball moving. So we've now managed to create a snake body, move the snake, and we've even managed to put our snake related code into a separate class. Now the next step is to figure out how to control the snake. Now we're going to control the snake by using the up, down, left, and right arrow keys. And we're going to be using our key bindings that we learned in yesterday's lessons to be able to translate this into a change in direction of the snake. In our code, right after we create our snake, we're going to call the screen.listen method to start listening for keystrokes. And the keystrokes that we're going to listen for are the up, down, left, and right arrow keys. Now those keys are described by a string. So it's a uppercase U and then a P. So this would be up, and then it's again uppercase down, left, and right. These are the keys that it will detect. Obviously the up, down, left, and right arrow keys on the keyboard. The function that you're going to bind it to is going to be a function in the snake object, and it's going to have the same name. So for example, it will be snake.up, and that will be triggered when the up key is pressed. And then the same thing happens with snake.down when the down key gets pressed, and then again with left and right. Your job is to have a think about how you can create these methods up, down, left, and right in the snake class so that when the up key or the down key is detected, you can move the snake and change its heading accordingly. So remember that up is going to be towards north, down is going to be south, left is going to be towards the left of the screen, and right is going to be towards the right of the screen. So have a think about the headings that we spoke about in previous lessons. And if you need to, it might be worth just setting up a brand new project, getting a turtle up and running, and then setting its heading from 0 all the way to 360 just to see which direction it's actually facing. If you manage to complete the challenge, you should be able to control the snake, and even though it's going to continue moving forwards, you now determine which direction it moves in by using the arrow keys. Pause the video now and see if you can complete this challenge. Alright, so I've already created all of these lines of code, which is going to get the screen to listen for these keystrokes. And then when it detects it, it's going to call these methods in the snake class. So inside our snake class, let's go ahead and create those methods. So we've got up, down, left, and right. Let's think about how we can turn the snake up. In order to turn the snake, the segment that we're most interested in is the first segment. That's basically the head of the snake. So we could tap into self.segments and then get hold of the 0th segment, which is the first one, and then change its heading by calling set heading. And then we can tell it to, for example, if it's up, then it should actually be turning to the 90-degree direction, which is actually towards north. Now I'm going to go ahead and put a pass on all of these other methods, just so that we can actually test our code and it doesn't give us any errors because these functions are currently empty. Now, if you don't have the pass, it won't like it because Python doesn't like the idea of empty functions. But now we can at least just test this one thing. So when we run our code, we should be able to hit the up key and you can see the snake change direction. Let me just do that again. And this is because we managed to get the first segment, the head of the snake, to change its heading to 90 degrees, and then the rest of the body will follow because it's continuously moving on every tick of the clock. So using this, we can now set the rest of the methods. But because we're going to need the head of the snake quite a few times in our code, it might make sense to actually create a separate attribute. So after we've created the snake, after we've got some segments inside this list, we can create an attribute called head, which is going to be the head of the snake. And this can be equal to self.segments at index 0. Now remember, if you have this line of code above the create snake, it's probably going to error out because at this point the segments is empty, and if you try to get the first item from it, it's not going to allow you to. So look at the positioning of the code here. Now, once we've got this set, we can go down here and change everywhere where we need to use the head of the snake. So for example, when we're moving the head forwards and when we're moving it up, left, down, and right. Now we can set each of these headings. Up is going to be a heading of 90. Down is going to be 270. Left is 180. And right is 0. These directions are just simply counterclockwise. So the turtle starts out pointing towards east, and that's a heading of 0, and then going anti-clockwise, up is 90, left is 180, down is 270. This can be easily verified just by testing out some numbers, right? You could just put some numbers in there and then just try it out and see which direction it goes, and then you'll be able to figure it out. But we've also mentioned this in previous lessons, so you could also go back and take a look at when we looked at the heading of the turtle. So now if I go ahead and run this, then you should see that I can now freely control the snake by going left or right or down or up. And if you manage to do this, then you should consider yourself successful. Now, while I was testing this code, I realized that there's something about the snake game that we haven't really accounted for. And it's the fact that the snake can't move back on itself. It can't go forwards and then go the opposite direction, because that requires the head to change directions. And this is not allowed in the official snake game. So how can we code this into our game? Well, we have to figure out when the head is pointing towards down direction, then we shouldn't allow it to go up. And similarly, when it's pointing up, we shouldn't let it go down. When it's pointing right, we shouldn't let it go left. So at the top here, I'm going to create some constants. I'm going to create a up direction is going to be 90. Down direction is going to be 270. Left is going to be equal to 180. And right is going to be equal to 0. So now that I've got all of these as constants, I can go in here and set the heading to instead say up when it needs to go up, down, left, and right. In addition, we're going to do an if check. So we're going to say if the current self.head.heading is not equal to down, Well, in that case, it's allowed to move up. So this way, it just means that if the current heading is pointed down, it can't move up. But for all other directions, if it's already moving up or left or right, then it can change the heading to up. Now, be really careful here because it's not just self.head.heading, it's actually heading as a method. Because remember that the head of the snake is the first segment of our list of segments, and each segment is an individual turtle. The turtle has a heading method which will give you a direction in terms of these 360-degree numbers, and then we can use that to check to see if it's equal to down, and if it is, then it's not allowed to go up. So using this logic, see if you can complete the rest of the 3 methods so that when you run your code, you can turn in all directions. But when you're facing one direction, you can't go backwards like this. All right, so it's going to be pretty straightforward. If it's already going up, then it's not allowed to go down. If it's already going right, then it's not allowed to go left. And finally, if it's already going left, then it's not allowed to go right. So this way, even though our snake can move freely through the space, it can't go back on itself. And there we have it. We've now managed to create our snake, get it to move, and control it using our key presses. Even though it seems like our game is still not quite there, we've already come so far. So this comes up to our hour mark, and it's now time to take a break, refresh your mind, look at some of the concepts that you might be confused about that we covered today, especially this concept of using the update to refresh the screen, as well as using the timer to delay the refresh so that we can control how often it happens, and then using our key bindings as well as separating our classes. We looked at a lot of things today. Now tomorrow, once you're rested and fresh and ready, we're going to be finishing up the snake game, and we're going to be learning about inheritance as well as slicing, and we're going to be building out the full functionality of this game. So I hope you're looking forward to it. I certainly am. I'll see you tomorrow. Now we've done most of the easy parts, getting a paddle and a ball up and running on our screen. The next few parts are going to be a little bit more tricky. And the first thing we're going to tackle is how to detect collision when the ball hits the wall at the top and the bottom and getting the ball to bounce. Now, we only need to detect collision on the top and the bottom walls, because when the ball hits the right or the left edges of the program, it should actually be caught by one of the paddles. And if it isn't, then that means that player has missed the ball and it's a point to the other side. So we need to focus on how can we detect when the ball has collided with the top or bottom walls. When has its position gone past a certain point that it probably is going to collide with the wall? We've done something similar in Snake, but it's again time to revisit this topic. Now, on top of that, we have to figure out how do we get the ball to actually bounce? And what does bouncing actually mean in terms of changing the position of the ball? When the ball is constantly going up in the Y value and going up in the X value in order to travel in this direction, what actually happens to the X and Y values when it bounces? Which one gets reduced and which one stays constant? Have a think about those questions and play around with some of those numbers and see if you can complete this challenge by yourself. If you get stuck or if you just want to check the answer, then come back and I'll go through the solution with you. All right, so it's going to be inside our while loop where I'm going to be detecting the collision with the wall. And in order to detect the collision with the wall, Essentially, what I'm going to say is that if this screen is 600 by 800, when the ball is at a Y position that is above 300, remember 300 is half of 600, and the Y-axis goes from 0 to 300 and 0 to minus 300. So once the ball is past 300, then it's going to be way past the wall, right? So at that point, I can be pretty sure that it's going to hit the wall or has already hit the wall. So that will be my criteria for detecting collision. So I can say if the ball dot y core is greater than 300, well, in that case, it's basically gone too far up and it's hit the top wall. Now, in addition, I can add a or statement to say if the ball.y core is less than minus 300, then that means it's gone too far down and it's hit the bottom wall. So in this case, it needs to bounce. So we need to figure out how to get our ball to bounce. And we're going to create a bounce method in our ball class in order to tell it how to do this. Firstly, we're going to need to figure out a new y, because the y coordinate needs to essentially reverse. So whereas previously our y coordinate was going up and up and up, increasing each time, when it hits the wall, it needs to reverse direction. So if it was increasing, it needs to decrease. If it was decreasing, it needs to increase. So basically, we need the opposite of what it currently is. To do that, the easiest way is to create an attribute, which I'm going to call X move, and another, which I'm going to call Y move. These are going to start out at 10, and every time we move our ball, we're going to say self.xcore plus self.x move and plus self.y move. This basically hasn't changed anything. It's just that every single time the ball moves, it's going to increase in the x coordinate by 10 pixels and also increase by 10 pixels in the y coordinate. Now, when we bounce, however, we need to change our y move so that it's the opposite in terms of direction of what it used to be. So if it used to be plus 10, we want it to be now minus 10. And if it used to be minus 10, we want it to be now plus 10. To do that, all we need to do is multiply it by minus 1. So that means if y move is currently equals to 10 and 10 is being added to the y coordinate, then this ball is moving upwards. But when we reverse the direction by multiplying it by minus 1, now that is now minus 10. So we're now adding minus 10 to the y coordinate, which is the same as subtracting 10. So this is some basic high school maths that's going to get our Pong program to start moving in the right direction. Now, back in the main.py, under these conditions, when the ball has hit the top or the bottom, we're going to get the ball to bounce. And now if I hit run, you should see that when the ball hits the top screen, it comes right back, exactly in the way that we wanted to. But the only thing that we might need to tweak is look at how far it's gone before it actually bounces. It's completely disappeared off the screen before it actually makes a bounce. So we can adjust these values accordingly. So I think it works best when we actually have it as 280. So remember that the width of the ball is 20 pixels. So if we're 20 pixels away from the wall, then that's pretty much where we need to bounce. So if I run this again, you can see that the ball hits close to the wall and then it comes right back. So this will take a little bit of thinking to get your head around it. The best way to really understand this is to print out the values of the new y and also of the y move, and also after you've modified the move in the bounce. Look at those numbers and you'll eventually be able to understand what's actually happening to the position of the ball. But effectively, all that we're doing is we're defining an amount that the ball is going to move by in the x and the y axis. We're adding that amount to the x and y coordinate in order to move the ball. And when the ball needs to bounce off the top and bottom walls, we reverse the y move number so that we get it to subtract instead of add. And that moves it in the opposite direction. So we figured out how to detect collision with the top and bottom walls and make our ball bounce off the walls. The next thing we need to do is to detect when there's a collision with the paddle and make the ball bounce off the paddle. This is probably going to be the hardest part of this program yet, so I want to talk you through the logic. Now, how can we know when the ball has hit the paddle? Now, normally we use the distance method to check what is the distance between the ball and the paddle, and if it's less than a certain amount, then we can be relatively sure that they've made contact with each other. So the code that we normally use would be something like this. We get our ball and we check its distance from the paddle. Now remember that our ball has a width of 20 pixels and our paddle has a width of 20 pixels. Normally we would say, well, if that distance between the two of them is less than 20, well then they've probably made contact, right? But the problem occurs when the ball hits the paddle, not right in the center, but at the edge of the paddle, because this distance measures the center of the ball from the center of the paddle as the distance. So you can see that this distance is way bigger than 20, so it's not going to register as a collision. How can we solve this problem? Well, we could add on an additional condition. We could check, well, if the ball has gone past a certain point on the x-axis, if it's gone far enough over to the right, and it's within a 50 pixel distance of the paddle, then that also means it's made contact with the paddle. Inside our main.py, I'm going to add a comment to detect collision with right paddle. So let's experiment with some numbers here and see if we can get the ball to bounce off the paddle. In this case, we're going to check if the ball dot distance to the right paddle is less than 50 and the ball dot x coordinate is greater than 340. If the ball has hit the right paddle, let's print something to the console to test our code. Let's print made contact. So if we run this code and I manage to make contact with the ball, you can see that it says make contact in our console. So instead of just printing make contact, what we want the ball to do is to bounce. Now this bounce is a little bit different from the last bounce because the previous one was changing its y coordinate so that it moved in the opposite direction along the vertical. But in this case, we actually want it to move along the opposite direction in the horizontal because the paddle's here and the ball's coming this way. We want it to go back this way. So instead of just calling this bounce, I'm going to right click on it and then refactor and rename to bounce y because this is bouncing in the y axis. Now, once we hit refactor, it'll change it here and it'll change it here. Now, on top of that, I'm going to define my bounce x. So bouncing in the x-axis. And this is very similar. We're going to change the x move, so the amount that the ball moves each time when the move method is called. And I'm going to multiply it by -1. So reversing the x direction. And then when our collision is detected, we're going to get the ball to bounce in the x direction. So now if we run our code, you can see that even though this only works on the right paddle, when the ball hits the right paddle, it moves back and it bounces back towards the left. It changes the direction that it was moving in the x-axis. So now let's add the collision for both paddles because they both need to bounce in the x-axis. And so we're going to tag onto this a or statement. And we're going to say, or if the ball dot distance to the left paddle is also less than 50. And on top of that, the ball dot x coordinate is less than 340. So this basically checks to see if the ball has gone far enough to the left as to be past the paddle and it's within a distance of 50 pixels from the left paddle. So if we run the code right now, you can see that not only does our ball bounce when it hits the right. So now when we run the program again, you can see that not only does the ball bounce on the right paddle, it also bounces when it hits the left paddle. Now, there's a little bit more tweaking that we can do with the coordinates, because you can see that when the ball hits the paddle, it goes a little bit too far before it actually reverses direction. So we can change this to a slightly smaller number if we want it to bounce before it's within the actual paddle. So we can change this to 320 and this one also to 320. And notice what happens now. Before it hits the actual paddle, it now actually bounces. And it doesn't look like as if the ball's fallen into the paddle before it turns back. And there you have it. Now we just have to figure out what should happen when the paddle misses the ball. For all of that and more, I'll see you in the next lesson. Now we're pretty close to the end of the program. We've managed to do pretty much everything other than detect when the paddle actually misses a ball. And if the right paddle misses the ball, then the left player gets a point. And this should trigger a restart of the game where the ball goes back to the center and starts off in the opposite direction. In order to do this, to detect when a paddle has actually missed the ball, effectively what we're checking is that the ball has gone past a certain point on the screen. So we know that we're already checking when the ball goes past this line and it's within 50 pixels of the paddle, then it should bounce back because that means the ball was caught by the paddle. But if it goes further than that, if it goes beyond that on the screen, like over here or over here, then that means it's a miss and we should reset the ball. Have a think about how you might create this behavior and as a challenge yourself, see if you can complete the code. So I'm going to add another comment here, which is going to be detect when right paddle misses. The right paddle has basically missed the ball if the ball.x coordinate is beyond 380. We know that the width of the screen is 800 and we know that the paddle is at 350. So the paddle basically goes from 340 to 360, and if it's already gone past 380, then the paddle has definitely missed the ball. So in this situation, we're going to get the ball to reset its position. And this is going to be a method in the ball class. So let's create it, and I'm just going to paste it in so I don't make any errors in terms of the naming. Resetting the position of the ball is going to involve getting the ball to go to the original position. So we can tell self to go to 0, 0. Now, if we run our code, you can see when the ball has gone past a certain point and it's not caught by the paddle, it goes back into the center. But we want the ball to go in the opposite direction once it's been missed by the right-sided player. It's time for the left-sided player to get a turn. So in addition to getting the ball to reset its position, we're going to get the ball to reverse its x-axis. So we're going to call self.bouncex. Now notice how when the ball gets missed, then its direction gets reversed. It starts off in the center and it goes off in the opposite direction. Let's go ahead and define the left-sided paddle miss. And we can do that by simply saying ball.xcore is less than minus 380. And in this case, we're again going to get the ball to reset the position. Now, the reason why I've got these in separate if statements is because later on we're going to need to detect when the right-sided player or the left-sided player actually gains a point. So when the right paddle misses, the left player gets a point. When the left paddle misses, the right player gets a point. Now, when the ball goes past the right edge and it's not caught by the paddle, then it starts off in the center and it moves to the left. When it's not caught by the left-sided paddle, it starts off in the center and it goes to the right. All that's left to do is to figure out how to do the scoring. And that is what we're going to do on the next lesson. To start, we're going to need to create a new scoreboard file. And then inside this file, we're going to add our usual imports and we're going to create the scoreboard class. Now the scoreboard class is going to inherit from the turtle class. So we can go ahead and add all of our inits and our super.init. Now let's define our scoreboard. It's going to have a white color, so it shows up on the black background. It's going to have pen up because we don't want it to draw. And it's also going to have its turtle hidden because we're only interested in it being able to write something. And the thing that we want it to write is the current score. Let's go ahead and create some attributes for this scoreboard class. One is going to be the L score, which starts off at 0, and the other is going to be the R score, which starts off at 0. So our scoreboard is going to keep track of how the left player and the right player are doing. And then it's going to write this onto the screen. So we're going to write the self.L score first, and we're going to change the alignment to center and also change the font to something quite large, like a courier font with 80 points and have a normal weight. Where do we want this to be written though? Because by default, this is going to be written at the center of the screen, 0, 0. But instead, what we want it to do is we probably want it to go to somewhere on the top left of the screen. This is the left player score. So you can have a play around with the coordinates, but I found that -100 in the x-axis, so a little bit to the left of the center, and then 200 on the y-axis, so near the top of the screen, seems to do well for this left-sided score. Now let's make this show up by going back to our main.py and importing our scoreboard class and creating a new scoreboard object. So when we hit run, you can see that big 0 show up right here. Now, the next thing we need to do is to show the right-sided player's score. We're going to make our scoreboard go to the opposite side of the screen. So that's going to be +100, and again with a y value of 200. And then we're going to get it to write the right-sided score, so our score, and we're going to have the same alignment and the same font. Now you can see 0, 0 when the game starts out. Now what we actually want our scoreboard to do is to keep track of the score. So when the right paddle misses, it's a score to the left-sided player. We can define that in our main.py. When the right paddle misses, then we're going to get the scoreboard to give the left side a point. So maybe we could have a method called lPoint in our scoreboard that increases the point in the left-sided player. So we can say self.lscore plus equals 1. In addition, we're going to need to update our scoreboard, but all of that code is stuck in the init. So let's go ahead and move it out into a separate function, which we'll call update scoreboard. And we can call self.update scoreboard when we first initialize the scoreboard, but also when we score a point. Now, when we run our code, you can see that when the right-sided misses, our left side gets a point. But at the moment, it's overwriting the previous score. So to prevent that, we have to add a self.clear before we update the scoreboard. And you can see now it erases everything that used to be there and it updates the score. So we've addressed when our right paddle misses, but what about when our left paddle misses? Well, we should have a method called rPoint as well that gives the right side a point. So let's add that over here. So we'll increase the R score by 1 and we'll again call update scoreboard. Now, when our left side misses, we get a point to the left, and when our left side misses, we get a point to the right. That's pretty much all of Pong. Now, if you want an extra challenge, both in terms of playing Pong as well as the code, see if you can figure out a way of getting the ball to increase its speed every time it hits a paddle, because that will make the game a lot more exciting instead of having it always move so slowly. If you can't figure it out, then continue watching and I'll show you the solution. So in order to speed up the ball, the key is in how much time we make our game loop sleep. Because the shorter that this sleep is, let's say instead of 0.1 second, let's do 0.01 second. And if we run now, you can see our ball moves a lot faster. Let's make it even more extreme and add another 0. So how can we reduce this number by a little bit each time, but never make it go into the negative? Because if this becomes a negative number, then we actually get an error over here telling us that the sleep length must be non-negative. In order to do this, we have to figure out a way of making this number a little bit smaller each time. So let's make this number an attribute in our ball class. Now, I don't want to call it speed because that might be a bit confusing because the turtle class already has a method called speed, as you can see here. So instead, I'm going to call it move speed and I'm going to set it to 0.1. So now inside our main.py, instead of having a hard-coded number, I'm going to get hold of my ball.moveSpeed. Now, every single time our ball bounces in the x-axis, it means that it has been touched by a paddle. So inside this method, in addition to getting it to reverse its direction, we can get the move speed to reduce by multiplying it by a decimal number. So I've stuck with 0.9 because that seems to work for me. So for example, if we start out with a value of 5 and we multiply that by 0.9, it becomes 4.5. And if we multiply that by 0.9, it becomes 4.05. So basically, each time the ball bounces on a paddle, it's going to increase in speed. But this can't go on indefinitely. When we reset the game, once one player has lost, we have to set this move speed back to the original 0.1, just so that it doesn't keep on increasing in speed indefinitely. So now you can see whenever the ball hits a paddle, it will increase its speed ever so slightly, making it just a little bit more challenging for the players. Now, you can of course tweak around with that number. So instead of 0.9, you could have 0.5, which basically halves the speed each time. But have a play around with that and see what you prefer. Now, one last thing to mention before we finish off today is that when I'm testing this program on my computer, it seems like when I hold down the up key or the down key, my paddle will continuously move. But there seems to be a bug with Turtle where if I hold down the W key, it can only move one bit at a time. But it doesn't seem to affect the S key. So I've been doing a bit of digging around online and I can't figure out exactly why this is. If you manage to figure it out, then feel free to add it to the Q&A so that other students can learn from it. But so far, I've been coming up empty. But this is just a warning in case you find this behavior as well on your computer and you get confused and thinking it's something wrong with your code. It's not. It's something about the Turtle module that causes it to behave like this. So don't worry if that's happening to you. And if you're playing Pong with a friend, you can always trick them to use the left-sided player.